So we're going to talk a lot about post-seismic deformation, and particularly in Southern California, and how that post-seismic deformation has affected how we measure geodetic velocities on the surface of the Earth and how we get fault slip rates from those geodetic velocities. And in particular, we're going to be looking at San Gorgonio Pass, which is actually highlighted in this picture for those of you that don't know. What this picture is showing is actually right in the center of the image is the San Gorgonio Pass, and it's this saddle between San Jacinto Peak on the left and the snow-capped San Gorgonio Peak on the right. And I actually just love showing this picture to people because it's a panorama of some of the most intense fault complexity in Southern California all in one picture. So in this valley in the distance, we have the main Southern San Andreas Fault running through Coachella Valley into San Gorgonio Pass. And then right in the foreground here, we're actually looking at the north-south trending faults of the Eureka Peak system. And then way off on the right, we actually see the western edge of the Mojave Desert and the Eastern California shear zone. So there's a lot going on in this area, faulting-wise, and we're going to dig into that a little more in a little bit. Just for reference, can you guys see my mouse when I move? Okay, great, thank you. Okay, so before we go any further, I want to make sure we're all on the same page with what I mean when I say post-seismic deformation. And what I mean is whenever an earthquake occurs, the Earth actually has to adjust to the new stress state that's been introduced. And so what you're seeing here is the classic elastic rebound theory model of the earthquake cycle. In the first panel, we have interseismic deformation, and that's where we have a locked fault at the surface. And along that locked fault, elastic strain builds up over time until the point that the strength of friction on that fault is exceeded, and then we have an earthquake. And that's when we enter the co-seismic period. And once the short co-seismic period is over, we enter the post-seismic period, or the after the earthquake period. And this is where a number of different mechanisms and processes help the Earth adjust to the new stresses that have been introduced by this earthquake in this co-seismic period. And these mechanisms are generally referred to as the ones you see here. So one of the first one is afterslip, and that usually occurs along the fault surface itself, usually around the area that was ruptured in the co-seismic event. And then we have poroelastic effects that can occur in the fault zone itself, but also around the faulting area. And last but not least, we have this broader scale process called viscoelastic relaxation, where the viscous material in the lower crust and upper mantle can flow in response to the stresses introduced by the earthquake. And that flow at depth can actually be measured as surface displacement. So I like to think of these in terms of their timescales. And on the right-hand side, afterslip and poroelastic effects are generally quite short-term. We're talking sort of minutes to maybe months. That might be a stretch. But on the other hand, viscoelastic relaxation is actually a much longer-term process, depending on where you're measuring it and how large the earthquake was. And so this process can last from months to years to decades to centuries, if you believe what I'm going to tell you in the future talk. So as we go forward here, when I refer to post-seismic deformation as a term, I'm going to be talking about viscoelastic motions primarily. We'll touch on a little bit of afterslip a little later, but whenever you hear the word post-seismic, think viscoelastic motion. So that's just for one earthquake, but when we actually look at an area like Southern California that has many earthquakes occurring over time, you start to ask the question of, what does post-seismic look like for each of these events? How is it different? Because each earthquake can have its own post-seismic processes. But more importantly, when we think about timescales, how many of these sort of longer-term viscoelastic relaxation processes are still potentially occurring in the modern day? So to sort of bring up some motivating questions, these are questions that I've been really interested in my PhD research and still am interested in. But first, how can we measure these potentially ongoing post-seismic motions from past earthquakes? Two, how does post-seismic deformation from these past events add up and potentially contribute to this modern deformation field that we're measuring? And lastly, can these motions affect elastic strain buildup on faults nearby? Can they affect seismic hazard? So these are sort of questions that we're going to cover a little bit in the rest of this talk. So we come back to this slide because there's one part that I forgot, well not forgot, but intended not to explain until this moment here. And that is what this little guy is on the surface. So how do we actually measure post-seismic deformation? How do we actually know it's occurring in the subsurface? And that is through the help of this tiny little cartoon GPS station. And so for those of you that aren't super familiar with GPS geodesy, I just want to give a quick overview. So space geodesy in general is a space-based tool that allows us to measure those tiniest motions of Earth's crust with very high precision. And this cartoon that you see here is a GPS station on the surface of the Earth, and this gray blob is its antenna. And what it's actually doing is talking to multiple different orbiting satellites at one time. So the Global Positioning System constellation consists of a number of different satellites that are constantly orbiting Earth. And at any given point on the surface, you can actually talk to multiple different satellites at that one time. So because of that, we are able to take the data that that station collects from all those different satellites and determine very precisely where it's located on the surface of the Earth. So we can do that for one time, but if we actually do that over time and determine its location for a period of years, we get something that looks like this. And this is the north component of a GPS time series. So on the x-axis, we have time and years. On the y-axis, we have northward motion. And I want to make sure we're all together on this because you're going to see a number of different time series moving forward. And so anything in the positive direction in a northward component GPS time series means you're moving towards the north. And anything in the negative direction means you're moving towards the south. And so each one of these circular dots here is a daily position measurement of the position of that one station. And over time, like you can see here, we can estimate a line fitting through these daily position measurements, and we can get a slope or a velocity. And so from this data, we can say that this station is moving at 15 millimeters per year in the northward direction. So we can do this for one station, but it's a lot more fun when we do it for a whole bunch of stations. And what you see here is the GPS velocity field for Southern California. And so each one of these little diamonds is a GPS station on the surface of the Earth. And it's really wonderful to work in Southern California because we have great station coverage, and that great station coverage allows us to have an awesome data set to study plate boundary deformation, but for our purposes, post-seismic deformation. So now that we've sort of covered the baseline material for what you need to know going forward, the rest of this talk is going to be broken up into two different sections. The first section is how have these past earthquakes and the deformation they produced, how is that deformation potentially affecting how we measure GPS velocities today? And once we sort of dig into that, we're going to take what we learned from that section and apply it to a specific area in Southern California called San Gorgonio Pass. And in particular, we're going to be looking at geodetic estimates of fault slip rate down there. But first, we need to understand how post-seismic deformation is affecting our GPS velocity field. So we come back to this diagram in order to ask the question of, if we were to put a GPS station right here in the post-seismic period following an earthquake, what would those post-seismic motions look like in a time series? How would GPS be seeing that motion? And to answer that question, we are going to look at a time series from station P511, which is sitting on sort of the eastern side of Joshua Tree National Park. And again, we have a time series, so time on the x-axis, northward motion on the y-axis. And so what we can read from this time series is that at the beginning, at year 2008, this station is sort of humming along, doing its thing, interseismically moving, and then boom, on April 4th, 2010, the magnitude 7.2 Elmira-Cucapat earthquake strikes. And this station, in response to that earthquake rupture, immediately moves towards the south. And after that earthquake break or jump, we actually see continued southward motion in this decaying pattern, this logarithmic or exponentially decaying pattern. And this curvature that you see is the post-seismic deformation signal. And so over time, this station is going to keep moving to the south, but that southward motion is going to decay more and more over time. And eventually, after a period of years, or maybe a longer period than we see here, the velocity is eventually going to match its pre-earthquake or interseismic velocity. So for earthquakes that we've observed with GPS, like the Elmer-Kukba event here, identifying this very conspicuous signal is very straightforward, and removing it is also straightforward. We can just fit it like we have here with an exponential or logarithmic term or some combination of the two. So, you know, when we see it in GPS time series, it's pretty easy to sort of identify and remove. However, when earthquakes happened in the past, we of course didn't have GPS stations back then to monitor their post-seismic jumps and early post-seismic motions. So even for earthquakes that can still have ongoing post-seismic signals, we have no simple visual way of identifying them. So as an example, this is a station time series for station WGPP, and this station sits in the southern end of the San Joaquin Valley, and it actually sits very close to the location of the 1952 magnitude 7.5 Kern County event. And this event was large enough so that it could actually still have ongoing viscoelastic motions. But again, if we look at this time series, all we really see is just sort of a flat line. We can't pull out any kind of post-seismic signal just by looking at the time series. So this brings us to the sort of so what, like why are we looking at this? Why does this matter? And in order to answer that, we need to define our goal. And our goal in this instance is to estimate time invariant, transient free crustal velocities. So we want crustal velocities that represent the steady state background plate velocity and don't have any of those post-seismic motions in them. And this comes with a sort of addendum or caveat that of course someone's signal is someone else's noise. And while yes, post-seismic transients can be very useful in studying the structure of our Earth and the lower crust and upper mantle, in this particular scenario with this particular goal, they're noise. We really don't want them. We want to remove them. So our sort of problem here is that we have over 2 decades of these awesome high precision GPS observations, but they're potentially biased by these ongoing post-seismic displacements and these transients. So these transients can cause an increase or decrease of GPS velocity, and that bias can then get folded into whatever estimated velocity field we get out of that GPS time series, and then it gets folded in again to whatever crustal deformation analysis you do with that data. And so the products that come out of those analyses, like long-term fault slip rates, strain rate estimation, and seismic hazard assessments, then have those post-seismic biases in them. So the bottom line here is that if we want these sort of long-term fault slip rate estimates, for example, we need long-term GPS velocities. We need those steady state, transient-free, beautiful straight line GPS velocities. To do this, we had to come up with a way to sort of remove it. And the way that we went about doing this was to forward model the earthquake time series that we knew of and then subtract it from our observed GPS time series. So fairly straightforward, right? We have this cartoon diagram to sort of illustrate the process. You know, we have our observations, our data, we forward model the earthquake displacements, we pull them out of the observed GPS time series in order to theoretically produce long-term GPS time series with no more transients in them. So this gets a little complicated because, as you remember, we're working in a plate boundary and there's a lot of earthquakes, right? So what you're seeing here are 217 magnitude 6.0 events and larger that have occurred in the historical record from year 1800 to early 2019. As a note, we do not include Ridgecrest in this assessment. And the question that sort of props up here is which of these 217 events actually matter? You know, which ones could have produced large enough displacements that we can still measure them in the modern day? And which ones could be then affecting our GPS time series based on our modeling? So to test that, to see which of the earthquakes actually do matter, we go ahead and forward model each and every one of them. So we model the viscoelastic motions from the time the earthquake occurred in the historical record to the end of our GPS time series, which is the year 2018. And to do so, we use this given viscoelastic model. And I'm not going to go into exactly why we chose this model. You're welcome to ask me later, but suffice to say, we have a 15-kilometer elastic crust, then that's followed by a Maxwell viscoelastic crust, and then 2 different Berger's bodies going down into the mantle. Once we model all those events, these are the 12 events that actually seem to matter, if you will, again, based on that particular model. So they're listed here on the right, and they're plotted here on the left, and we'll dig into this plot in just a second. But these are the 12 events that have measurable GPS displacements in any year of our time series, so any year 2000 to 2018. And we define measurable as having greater than or equal to 0.35 millimeters per year of motion in any year of that time series. So on this left-hand map plot you see here is actually plotting for the year 2018, the extent of measurable viscoelastic post-seismic displacement due to just that earthquake. So to break that down a little bit, if we were to zoom in and just look at the 2012 Baja California earthquake down here in the south, anything inside this red double couple lobe structure means that we can measure the viscoelastic post-seismic motions caused by that earthquake. And anything outside that the lobe structure line means it's no longer measurable with GPS instruments. And for some of these events, it's not a huge shock that the more recent events still have a decent spatial effect. So 2010 is still covering a wide area. The 1992 Landers and 1999 Hector Mine events are still very much present. But the ones that sort of knocked me over were the 1906 event, which you can see in light blue. And the extent of these measurable motions goes all the way out to southern Utah and northern Arizona. And it's the same story with the 1857 Fort Tejon event. And these two events were some of the largest we've ever recorded. So perhaps it's not hugely shocking that they were large enough to perturb the lower crust and upper mantle in such a way that those post-seismic motions are still not only going today, but very much measurable in large parts of both California and the sort of Southwest. So pretty cool. It sort of blew my mind when I first plotted this up. So now that we've decided which of the events actually matter the most for our GPS time series, we're going to go ahead and subtract them. So those 12 events, we model them out to the time of our time series and subtract what those end year time series period motions would be for each earthquake. And when we do that, we get our post-seismic reduced GPS velocity field, which looks like this. So this is essentially our corrected velocity field, if you will. And I'm not going to force you to stare at this field for too long because if you don't, look at these every day of your life, you won't see the tiny, minute changes that have happened. So instead, in the next few slides, we're going to break down what actually changed and what worked, what didn't work when we did this correction. So the first thing we're going to look at is another time series. And this is actually the same station we were looking at before. But this time, we're plotting on the top the observed motions. And you can still see the Elmore-Kukapa earthquake is well represented with its earthquake jump and its post-seismic motions here. On the bottom, however, we're plotting our post-seismic reduced or our corrected time series. And as you can see, the visual sort of assessment looks really good. We're able to remove the jump and able to remove pretty much all of the logarithmic or exponential motion that we have modeled here. So we're quite encouraged by the fact that it looks just as we were hoping it would. And you can see the difference in velocity here. So for the observed time series, we get a velocity estimate of about 1.7 millimeters per year. And in the corrected one, we get an estimate of about 2.7 millimeters per year. So a millimeter difference doesn't sound like a whole lot, but if you think this is just sort of one station out of a whole network of stations, like that can actually start to add up based on how you use the data and what kind of modeling assessments you do. So if we go ahead and look at how our whole network fared with this correction, we get a plot that looks like this. So we did an analysis of just the Elmore-Kukapa earthquake to see how much post-seismic amplitude and post-seismic signal we were able to remove from the observed time series. And so essentially we just compare, the observed time series with the corrected time series and say how much post-seismic was left over in that corrected time series. And so in this color map here, anything in blue or anything in cool colors means our model did a good job and we were able to remove a large portion, if not all, of the post-seismic motion that was in the observed time series. Anything in a warmer color means that we struggled a little bit more. Our model didn't quite do the job, as it were. And in particular, when we started to ask, why are there these high residuals down in the southern end of our network, we came up with the idea that since our modeling doesn't have any accounting for afterslip, perhaps what we're seeing in these high residuals down to the south, near the location of the Elmeyar-Kukapa earthquake, perhaps all these high residuals are actually afterslip that we haven't accounted for, but it's still present in the corrected time series. So that's what sort of our hypothesis is when it comes to looking at this particular color map. But overall, we're able to remove up to 60% of the post-seismic amplitude with this particular methodology, which we feel pretty encouraged by, we're pretty happy with. When it comes to looking at what we actually took out, I think this is where things get even more interesting. So what you're seeing here is essentially our residual field. So we take our observed GPS velocity field, we subtract the corrected field and produce this map. And in the color map itself, anything in those sort of warm colors means we had a lot of high residuals, and anything in those cool colors means we had fewer residuals. But for me, the most interesting thing about this plot is that it actually shows how each of the post-seismic deformation fields from each of these earthquakes constructively and destructively interfere with each other. So when you add all of these if you think of each earthquake as a layered grid of displacements, and you were to add them all together to see what just the post-seismic looks like in this area, this is what you would get. And I'm not going to compare them each for you now, but when you actually go and compare each of the separate gridded displacements for each earthquake with this map, these 5 events I've listed here are the ones that seem to dominate the shape of this field the most. So again, not a huge shock that sort of the 2010, the 1999, and 1992 earthquakes are still dominating the field. Like, you can just look at the Eastern California shear zone, southern Mojave here, and see, that's exactly where Landers and Hector Mine happened, right? So no big shock that those are still having pretty large seismic displacements or post-seismic displacements. But what surprised me more was that the 1952 Kern County and the 1857 Fort Tejon events still seem to have an effect on the shape of this deformation field, this post-seismic deformation field. So it sort of points to the fact that these past earthquakes can still be having an effect on what's going on today. So to sort of set you up with some key takeaways from this section, bottom line, yes, earthquakes are still affecting the GPS velocity field. We can sort of talk about, which of those earthquakes, depending on how you model them, can be affecting it today. But for sure, there's still some serious post-seismic effects in the GPS velocity field today. And of those original 217 events, 12 of them in particular seem to be having measurable post-seismic displacements. And last but not least, we've created a new post-seismic corrected GPS velocity field for anyone who wants to use it. So if you're interested in this kind of data, please feel free to visit our paper. We have a lot of supplementary materials that are we welcome use and conversation about. So that's how post-seismic deformation is potentially affecting our GPS velocity measurements. And now that we've talked about that, we're going to take that post-seismic reduced velocity field, that corrected field, and we're going to apply it in Southern California to estimate geodetic fault slip rates. So before we actually get into the specifics of the modeling, I want to set up why people care so much about San Gorgonio Pass. And so this map is showing you where San Gorgonio Pass is located, and it's right in between the San Bernardino Mountains to the north and the Peninsula Ranges to the south. And it really is a saddle in between 2 decent-sized mountain blocks. And everything plotted in black is a fault. And not only just a fault, but an active fault, or a known to be recently active fault. And so what you're seeing here is one of the most complex areas of faulting in Southern California. There is a lot going on here, and I'm going to try to break down briefly what could be happening in this particular area. One of the main reasons that people are most interested here is that running through the center of this image is the granddaddy of Southern California tectonics, the San Andreas Fault. And this fault trace has been the main conductor of plate boundary slip for the last 5 million years or so. And so it's, in geologic history, it's had really high slip rates. It still has high slip rates today in some areas, but people are haggling over what is actually happening in San Gorgonio Pass, because as the San Andreas approaches the San Bernardino Mountains block, it splits up into multiple different strands, and each of those strands can have a different slip rate. Another reason why everyone, particularly active tectonicists and seismologists, talk about this area is that it's possible and potentially likely that the next large magnitude earthquake on the San Andreas might initiate down here in the Salton Trough and rupture towards the north, potentially through San Gorgonio Pass and then into the bowl full of jello that is the LA Basin. So we kind of want to know what these faults are doing and whether they have the capability of accommodating a huge rupture. And to answer those questions, we need to know what each of these faults is doing activity-wise. And so geologists today have sort of two camps in a debate about the activity levels of these two faults. And on one camp, they believe that the Mission Mill Creek fault, which is this fault to the north, this strand to the north, is active today, has been active in the Pleistocene, and there's evidence that it's still slipping in the modern day. Everyone generally agrees that this southern fault here, the San Gorgonio Pass Thrust and Banning Fault, is active today. So we're generally agreed that that's definitely something we need to worry about. But this Mission Mill Creek fault is up for consideration, up for grabs about what's actually going on. So again, in this one camp, people think it's active today. In the other camp, they think, heck no, definitely not active. It's been inactive for the whole, Quaternary period. What are you even talking about? So those are two pretty end member scenarios for a fault, and it really sort of adds to the level of, we need to figure this out. Like, why are we disagreeing, and can we come together on anything about these two different systems?
Catherine, have you heard about the riddle faults? Those faults that are in between of these faults, and you have like diagonal things?
In actually San Gorgonio Pass?
Yeah.
I've heard about them, but that's like a whole nother level of complexity that I'm not getting into here, but it's a good point to make. Like, you can go down a couple more levels of like faulting here. I'm serious, this area is crazy. And that actually feeds into the point I'm about to make, in that, just San Gorgonio Pass itself is crazy, but then we look at everything else around it. So there's a very likely possibility that fault slip and fault strains actually transferring around this San Gorgonio Pass knot, this knot of faults. And so one of these mechanisms could be this million years old block rotation system off in the eastern transverse ranges. It's been rotating clockwise for the last 6 million years or so, and could still be happening today, potentially. There's also the emerging fault hypothesis, where this fault is hypothesized to follow the trace of the 1992 Joshua Tree earthquake and the 1992 Landers event, and that could provide a direct connection to avoid San Gorgonio Pass and connect between the southern San Andreas fault and the eastern California shear zone. And last but not least, there is of course the San Jacinto fault off to the west, which we know is working on becoming a total through-going fault in the last couple million years, and could again provide a transfer mechanism right around this knot of faults in the area. So this sort of adds to the complexity about, how do we know what's going on here? We really want to figure this out. Can we learn anything with geodesy? And that's what brings us here. So to try to attack this sort of many-faceted problem, we basically decided to use elastic fault block modeling with our geodetic data. And for elastic fault block modeling, there's a few different programs out there that you can use. We decided to use TDefNode, which is written by Rob McCaffrey. And the first step is to define your block geometry. And you have a decent amount of freedom with TDefNode to determine whatever kind of geometry you want. You can have dipping faults, straight faults. You can really go bananas with what you want to include, what kind of complexity you want to include. And once you're happy with your geometry, we go to the next step and we apply our data field. In our case, we use our post-seismic reduced GPS velocity field, as well as our observed velocity field, to compare the effects of those two. And then we reach the actual modeling stage. So we basically say to the model, okay, run an inversion that, says at this point where this GPS data point is located, find a velocity that gets as close to that GPS velocity data point as possible. And as the program does this, it actually estimates Euler poles for each of these blocks. And the rotation defined by that Euler pole defines the relative block motion, and that is our estimated fault slip rate. And once we actually run that inversion, once the geodetic estimates are estimated, we compare them with geologic observations from the field. So I want to make it very clear that we're not including geologic constraints here. We're just comparing them after the fact. So like we talked about before, there's a lot going on here. And because of the sort of geologic complexity that's already well known, we decided to focus on geologic fault expression at the surface to build and define our block boundaries. So we convert this map here into the block geometry you see here. And so this is our most complicated block model. It's got 16 different blocks, 31 different faults, and it uses 192 GPS stations, only horizontal components. And each block we tried to define in such a way that we could have at least 3 GPS stations for each block, so we'd have a solid constraint on its motion and rotation. So this is our most complicated block geometry, but we actually went bananas and decided to define a whole bunch of different geometries that each capture a question about activity in this area. So each one of these block hypotheses tests the activity level of a particular fault. And these range from our most complex model up at SGP1 in the upper left corner, which has got 48 Euler pole parameters and 16 blocks, to our least complex model, which is SGP16 down in the right-hand corner, and that's got 5 blocks and 15 different Euler pole parameters. So I'm not going to go through each and every one of these, but suffice to say, each one tests some sort of hypothesis about the area. When it comes to our data sets, like I said before, we're using our post-seismic reduced GPS velocity field, and in addition to our observed velocity field, again, so we can compare the effect of that post-seismic motion. But one plug I do want to make is that we were very lucky to be able to collect and include a whole bunch of campaign measurements. So these areas that are circled here, each have their own GPS campaign network, but these stations are invaluable because these are both areas that have a lot of remote wilderness and they're very difficult to access. So having these extra campaign stations really helps us constrain these fault slip rates. And if you're curious about this data and want to even use it for your own analysis, it's totally available at UNAVCO, so feel free to just dig in. When it comes to geologic data, again, we're lucky that we live and work in Southern California, and there's been so much work done on estimating geologic slip rates. And each one of these circles is a geologic slip rate study using either like paleoseismic measurements or offset tectonic geomorphologic landforms, that kind of idea. And we break them up into Pleistocene slip rates, which are sort of that older geologic time period, and then the Holocene geologic slip rates, which are the most recent geologic period. So kind of there's slip rates that sort of image or observed slightly different timescales. So we wanted to sort of make a distinction there and see what we could learn by comparing them separately. When it comes to actually learning about how we actually fit well with the data, how do we measure fitness in general, we first, our fit to the GPS data is pretty straightforward. It comes straight from the TDEF node model. We just use a reduced chi-squared score, and it's calculated as so, and that's really, it comes out of the model. It's how the model determines which inversion step is best. So really easy to say, okay, this model has a lower reduced chi-square score than this one. When it came to the geologic data, we decided to calculate our own root mean square score, and it's calculated in this way. And we calculate these scores again after model runs, so we don't have geologic constraints in our data. So now we get to sort of the results of everything we've just been explaining. And because we have such a large result set, if you will, we tried to probe it with really specific questions. And these aren't even half the questions I had about our models. So if you're curious about anything, any fault in particular, or what we learned about any specific area, please ask me, okay? And to start off with, we're going to look at, which fault geometries actually fit the data best, and what can we learn about those activity levels of the San Gorgonio Pass faults in and around San Gorgonio Pass itself. And second, we're going to talk about how the post-seismic deformation ended up affecting our geodetic fault slip rates. So that's sort of like my title of my talk is going to be represented in that question. And last but not least, we're going to tell the story of how we were able to assess and potentially resolve a known geodetic geologic discrepancy in the Eastern California shear zone. So first and foremost, which models fit the data best, right? And this is our best fitting model to the GPS data. And in addition, it's also our best fitting model to the older Pleistocene geologic data, which is interesting. And I won't make you stare at this for very long, but it represents all faults in the model except a very small fault in San Gorgonio Pass called Galena Peak Fault. And these are the slip rates we essentially get out of this best fitting fault geometry to the GPS data. But what I want to do is break down what the best fitting models for GPS data are. And these are the top 3 best fitting models for the GPS data. And what we see when we look at the top 2 best fitting are that each of these models actually prefers to have 2 active strands of the San Andreas fault running through San Gorgonio Pass. So that's this purple fault here and the red fault of the San Andreas. And there's a little star here, and that's because there's a small caveat, and that is that even though these models prefer to have 2 active strands there, the rates along this controversial, debated Mission Mill Creek fault are very low. We're talking 0 to 2 millimeters per year. And this is coming to us from all our GPS data. And so this sort of makes me wonder, is there room for reconciliation here between these 2 camps where some people think it's definitely active today, some people think no way, it's not active at all. And we know there's evidence to suggest that the Mission Mill Creek fault was active in the Pleistocene. And so maybe it was fast in the past and it's been slowing down over time and it's moving very slowly in the present. And to top it off, if you've ever been to this area, this is actually one of those areas that's very rapidly eroding. So there's a ton of uplift and a lot of, actual erosion and just a lot of, you can basically cover up the evidence for the geomorphic evidence anyway for fault slip by having such rapidly eroding terrains. So this makes me think that there's room for at least negotiation, maybe not a full reconciliation, but maybe we can get together on a couple of the facts here. When it comes to our other data types, this is the model that best fits our combined geologic data. So this is both the Holocene and Pleistocene slip rates together. And this fault does not include a blue cut fault, which is off here in the Joshua Tree National Park area. And last but not least, our Holocene geologic data is best fit by this particular fault geometry, which again does not include a blue cut fault, nor a Galena Peak fault, which is over here in San Gorgonio Pass, and it does not have a West Pinto Mountain fault here. And I won't go too deeply into this, but this is actually very interesting because some recent geologic investigations along both the West Pinto Mountain fault and the Blue Cut fault suggest that they're no longer active today. So the fact that we might see some sort of agreement between Holocene geologic data information and what the GPS data agrees with, it's interesting. It's a food for thought, if nothing else. So when it comes to actual post-seismic deformation and how that gets folded into our geodetic fault slip rate estimates, it's the way I try to really hammer home this message because I think it's really interesting, and I've written it for you here, and it sort of boils down to when we include post-seismic motions in our GPS data, GPS velocities, that gets folded into the geodetic fault slip rates and appears to increase them across nearly all our model faults. And so to sort of show you a figure that illustrates this, we're going to compare the slip rates generated from our observed velocity field that includes the post-seismic motion with our slip rates that are generated from our corrected field that has no post-seismic motion. So we're going to subtract one from the other, essentially. And when we do that, we get a figure that looks like this. And so anything in a warm color means that post-seismic motion caused an increase in slip rate along that fault. Anything in a cool color means that post-seismic motion actually decreases the slip rate at that location. And any fault that doesn't have any color at all means the change was so minimal it was within the error of our geodetic slip rate estimate. So you could just look at this map and see that in general, what you're seeing are warm colors here, meaning that most of the faults in our model seem to experience an increase in fault slip rate caused by this post-seismic deformation signal, with the notable exception of San Gorgonio Pass, which is sort of interesting to see. And this brings me to what could be described as sort of pushing the envelope a little bit, maybe sort of, I might sound a little crazy if I talk or explain what I'm thinking here, but generally when we talk about seismic hazard assessments, right, we think faster fault slip rates generally means a higher seismic hazard. So the fault is moving faster, it's generating more earthquakes, higher hazard. If post-seismic motions are somehow able to increase the amount of strain that's being accumulated along these faults, could they be increasing seismic hazard? And if they are, we know post-seismic motions decay over time. So are they introducing some sort of time-dependent seismic hazard? And should we try to assess that? Is there a way we can see how these post-seismic motions affect faults around where these earthquakes occur? So I don't have an answer to these questions, but it's something that I have been thinking about a lot recently and think it's potentially worth investigating further. So when it comes to the last bullet point here, can we resolve a known geodetic geologic slip rate discrepancy in the Eastern California shear zone? And the short answer is yes, but I'm going to give you the longer answer right now. So for those of you who have no idea what I just said, in the Eastern California shear zone, which is plotted here in this map in this red circle, sort of the southern Mojave area, or really the whole Mojave Desert, there's been this long-standing debate between geologists and geodesists about how much slip is actually being measured along these faults. And geologists think that the summed slip rates across all of these faults in the most southern Mojave here are about 6 millimeters per year, while the geodetic slip rates say, oh, it's about 12 to 13 or more millimeters per year. So that's double that of what geology is seeing. So definitely a point of disagreement between one field and another. And I have a little star here for another caveat, and this could be a very long discussion, but there's a very important question to ask, and it's, should these rates even agree? We know geodetic timescales are decadal, and we know geologic timescales can vary from thousands of years to even millions of years. So based just on that, we know that these two different fields and data sets could be imaging very different parts of a long-term plate boundary cycle. But, another caveat, why would some areas agree just fine and not others? Like, what's special about those areas that don't agree? What can we learn about studying those particular areas? So that brings me to looking at what our modeling says about this discrepancy between geologic and geodetic slip rates. So here are the numbers. The geologic rates give a range of about 4.4 to 9.5 millimeters per year. The geodetic rates, generally 12 to 13, though it depends on the model that you look at in the literature. When it comes to our modeling, our post-seismic reduced, our corrected field produces a summed slip rate of 12 millimeters per year. And our observed GPS velocity field with the post-seismic included gives 19 millimeters per year summed slip rate, which is a lot. And this sort of tells us that removing just the post-seismic, it helps bring it closer to the geologic rates, but it really doesn't do the trick. It doesn't really fix everything. And I was hoping it would. It was one of my hypotheses when I started this project that maybe post-seismic would solve everything, right? But it's not the case. However, when we include off-fault deformation and we account for off-fault deformation in addition to our post-seismic correction, geodesy fits just fine with the geologic slip rate range. So again, on the left, we're seeing our corrected field and slip rate estimates, and that summed slip rate is now 7.2 millimeters per year when you include off-fault deformation. And on the right, we see that without the post-seismic correction and just including off-fault deformation, the rate still isn't low enough to map geology. So if nothing else, this points to the importance of really understanding the processes that are ongoing in this area, but also off-fault deformation really needs to be very well defined and understood in these areas of discrepancy. So that brings me to my last slide, which are just the key takeaways from this section. The post-seismic deformation does appear to increase estimated geodetic slip rates when it's left into the velocity field, which potentially could have implications for seismic hazard assessments, but definitely an open question. Our models seem to prefer 2 active strands in San Gorgonio Pass, but that northern controversial Mission Mill Creek strand is moving very slowly in our models. And last but not least, when we remove post-seismic and we account for off-fault deformation, it appears to solve a discrepancy that's been sort of long-standing between geology and geodesy. And with that, I think, yeah, I want to thank you for your attention. Thanks so much for tuning in, and I'm really happy to take any questions you have. So thanks so much.
Thanks, Catherine. That was a wonderful talk. If anyone has questions, you can either drop them in the chat or raise your hand and we'll get to them. I might start with a question, Catherine. I'm wondering about your forward models where you're modeling your post-seismic decay. How sensitive is that to sort of that viscoelastic structure that you picked? Like, is it super sensitive to that or not so much?
So that's a great question and certainly an arm of ongoing research. I did not test other viscoelastic models with this particular research direction, but that's something that absolutely needs to be defined better. I don't have a good answer for you on that, but I'm really interested to see the answer once I figure it out. But.
Cool. Any other questions? Looks like we have one from Kang Wang. Do you want to ask it yourself? You can go ahead and unmute yourself.
Thanks. I just tapped in. So my question was, how do you account for the off-fault deformation in your block model?
So we only accounted for off-fault deformation in the Eastern California shear zone because there was a previous estimate by Herbert et al. 2014. And so we were able to just use the work they did to just apply it to the Eastern California shear zone. So it is not applied everywhere in our block model, but that would be another great thing to build in for the future.
Awesome. It looks like Tianzin, you have a question?
Yeah. Oh, sorry, I was muted. Yeah, I'm muted. Great. Thank you for the talk. It's really great. And I'm kind of curious about why the geologically measured slip rate can be comparable to the geodetically measured ones. Because if I get it correctly, the geologists measure the slip rate by measuring the offsets on the fault trace, which are created by a series of earthquakes. Whereas if I understand it correctly, the way geodesists or the way you measure the slip rates on the faults is by measuring the secular deformation on the faults. So those two are essentially created by 2 different processes. One is by aseismic deformation. The other is created by earthquakes. So why those two, should be compared, or why they represent the same kinds of deformation?
Sure. Yeah. So that's actually a fascinating question, and it's something I've thought about a lot. And one sort of way to answer your question is to ask, when you think about plate boundary deformation over time, we have these rates that we think about on the outsides of the plate boundary that are moving at, a certain X amount of plate boundary motion. And that's what we measure with GPS. So for, Western North America, the San Andreas Fault, imagine 50 millimeters a year of motion. When you measure it, the Pacific plate relative to the North American plate, that's how fast all those faults should be added up to accommodate. But when a fault actually accommodates that motion, how else can it accommodate it without earthquakes, right? So over time, wouldn't all that earthquake displacement build up to the slip rate we would see that would add up with all those other faults to that plate boundary motion? So that's how I kind of think about it when I compare these sort of geologic slip rates with geodetic slip rates. But there's definitely still a slight disagreement there because we're measuring slightly different things, right?
Yeah, right.
So
Yeah.
I definitely recognize that, yeah.
Yeah, that makes a lot of sense. Thanks.
Sure.
Awesome. Dave, looks like you have a question as well.
Yeah. Some of these geologic slip rates can be very small, very, very small. And when you do the inversion, how do you prevent your model from going it backwards? In other words, the geologists know that the fault's right lateral, but your modeling might try to make it left lateral.
Yes, that's it. It definitely happens. So we basically kind of throw out the results that, you know, if a fault that we know to be right lateral starts to go left lateral, we say, okay, that's not a valid, but we do that after the modeling actually occurs. So we don't have an input in there to, there probably is one now to think about it, but we don't include that in the actual modeling process.
You couldn't put a hard constraint in there, I guess.
Yeah, you could, but we did not.
I guess I have one more question about the locking depths. How did you constrain the locking depths on all these faults? Because some of them are different and there's sort of a trade-off sometimes between slip rate and locking depth.
Absolutely, there definitely is. And the way we decided to go about doing it is just to choose the depth of seismicity for each of these faults across the whole model network. There are different ways one could do it, but we decided just to go with that. I think we used the Hoxton 2000 seismicity profiles to decide that.
And it looks like Yuri also has a question.
Yeah, so the San Andreas is likely dipping in Coachella and almost certainly dipping in San Gorgonio. So are you accounting for these non-vertical fault geometries in your block models? And if so, how do you do that?
So we took, I guess I forgot to mention, but we take the subsurface fault geometries from a combination of the USURF fault models and the SCEC community fault models. And for the Coachella Valley dip, we have it dipping slightly, but we actually had some reviewer feedback in our paper that it should be dipping, you know, all the way to the surface or not. And so we did a test case to see how much that dip would affect the final parallel slip rate we got out of that. And it didn't end up affecting it too much. But for the actual fault geometries we define, we take that information from the SCEC community fault model and the USURF fault model. And I think for Coachella, we have a partial dip of 60, and in San Gorgonio Pass, we get down to 25 degrees dip. So those are sort of the low end estimates, but.
Yeah, I'm a bit surprised. We had a study looking at the effects of this fault dip. So basically the effect of the fault dip will be to offset the edge of the dislocation at depths where it transitions from creeping to locking. And it had something like 5 millimeters per year effect on the estimated long slip rate.
Yes, I think one of our viewers was Eric Lindsay, and he mentioned several papers that had your name on them for sure. And we read sort of the results of your guys' study. And I think for the TDEF node modeling scheme, its structure, we only estimate the dip slip and parallel slip rates. We don't actually estimate any opening or closing tension. And when you do that, we don't really have a huge effect or see a huge effect from dip angle for those slip rates. But at least for the case study we did not see more than varying maybe by a millimeter or so in the slip rate.
Okay.
But I can look into that if you want a more direct answer.
Sure, and I have another quick question. So to correct for transients, you're using a model that was calibrated to some extent using something like 10 years worth of data, but you're making the corrections on a time scale of centuries. And my question is, how do you know that you're actually making the corrections versus introducing epistemic biases?
That's a great question. We don't assess that here. This is sort of a test case scenario to see what happens when we try to account for this. So I can't say that we've assessed that effect. That is something that we should assess in the future. And that would probably feed into some sort of assessment of how much that viscoelastic model affects the actual velocities we get out of for those post-seismic motions for each of those events. So definitely future work. We haven't done it yet.
All right, thank you.
And Ignacio, looks like you have a question.
Okay, Catherine, wow, excellent presentation. Very nice.
Thanks.
So I have the question I did before about the riddle faults is basically because I had a discussion with a geologist talking about the Palu earthquake, because I did a tsunami study in Palu.
Oh, yeah, okay.
And actually, I would think that still there is an enigma about what happened within the bay, because basically this Palu earthquake, if you see the INSAR data, you can see that you have two faults almost parallel, one to each other, and in the middle you don't know what is happening because basically you have water. So I wonder if actually the post-slip analysis can actually reveal what is actually going on in the middle of the bay. I would think that someone is actually studying that thing, but it would be super cool. And I understand that there are some GPS stations around, especially from French people. Bini, I think he was managing some stations around, but we never had access to that one. With Jennifer, we were trying to do that.
Okay.
So it would be super cool for you to do something with that, maybe.
Sure, yeah. I'm always looking for new things to look at. But if you're saying if it's underwater, then do you even have GPS stations defining in between those faults that you see in the INSAR?
You have some station around the bay. So I would think that maybe with the station, you can do something in order to say, okay, this fault is actually having this behavior, or you have that geometry within the water.
Sure, there's always, yeah, we can definitely look into it. That'd be interesting to see what it would actually tell us. Definitely. Good suggestion.
Is there any last questions?